Hi, this is Talip Ozturk. I'm the founder of Vectroid. Vectroid is a vector database that is designed to scale to billions of vectors. So we're going to be talking about 10 things I hate about vectors. Before that, though, a little bit about me. I'm a Turkish software engineer living in the Bay Area for the last 12 years. I'm also the founder of Hazelcast, which is an in-memory distributed database used by almost all major US and European banks, and also the companies like Amex, Visa, and Apple. I was lucky to be part of Google Cloud AlloyDB team. AlloyDB is a distributed, scalable Postgres database service. And right before Vectroid, I was also head of engineering at Vectara. Vectara is a end-to-end RAG solution. And when I was at Vectara, we had to deal with hundreds of millions of vectors. It was super challenging to index and query. Dealing with hundreds of millions of vectors was very problematic. And I decided to solve this problem for the rest of the world with Vectroid. The title of the talk comes from a movie named 10 Things I Hate About You. We're not going to talk about you. We're going to talk about vectors, and not even 10 things, but 7. And hate is a strong word. I'm not a hater. I'm a lover, not a hater. So we're going to talk about 10 things, 7 things that bothers me, or 7 things that I found it very challenging. Um, so the vector is a new data type. It's way more complicated than like a Boolean data type or a double data type. Obviously, it's way more complicated than that. It takes way more space. It requires way more CPU to index. So it's way tougher than those like simple data types. That's why do we need a new database? Isn't it just another data type? Yeah, it's just a new data type, but it's a really difficult one. Okay, compared to integers and longs and doubles, float arrays, it's a very complicated to deal with. Okay, it takes way more space and more computation, more CPUs to index. But you still, though, if you have only like a few million vectors, so then it's not a big deal. So any vector database that you would choose, even PG vector will just do fine with a few million vectors. So it's perfectly fine. And this talk is not about that. This talk is about scale. So talking about hundreds of millions of vectors, if not billions. And when you're talking about scale, we're trying to also balance the cost, accuracy, and speed. So if you say I'm going to put everything into memory, then your cost will be high. But if you say, or I'm gonna use a binary quantization for every data set, that way my cost will be lower and my speed will be significantly better. Then you give up on accuracy potentially, right? So you're trying to balance all three while scaling to billions of vectors. That's what's challenging. So, so let's say you picked your vector database, you deployed it, everything is ready to go. What do? What I did was, okay, loading data. So I had vectors and I started loading. So if you start loading with Upstart API, it's going to take a lot of time. Okay, so you can speed it up by batching, right? Like batch upstarts are better. Yes, that's way better now, but still I have to deal with all the failures and all those cases, and it will still take way more time. What's the best one? The best one is bulk upload, of course. Just zip up everything, all the vectors, all the fields, and create one giant file and upload that file into the vector database. And as soon as you're done with the upload, you're done. Like it's a fire forget after that point. Yes, your database still can process it. It will take probably a little more time after that too, but still for you, it's done. It's a fire forget. And potentially your database can support terabytes of data. So you're not limited to a few gigabyte or something, then it potentially, if it can support like uploading at a speed of gigabyte per second, this is insane. This is going to be so good. So make sure to use bulk upload if you can. Okay, so that's the lesson that I got. Otherwise, the life will be miserable if you try to upsert with an API like hundreds of millions of records. Okay, that's going to be miserable. Don't do that. Um, okay, so as soon as you upload stuff, now it's time to index. So as we talked about it, the float array is a tough data type to index, and it will take time, and we know that. So it can take minutes, hours, sometimes even days. So one thing that you will immediately hear, like, oh, GPU is the answer. Just go buy GPUs and do vector indexing with GPUs. Everything will be fine. Not really. So GPU is great. GPUs are, I don't have any problem with GPUs. GPUs are great for the vector indexing, but they're not great for the non-vector fields. And usually you will have non-vector fields, and you will even potentially have full text too. And GPU will not help you there too. So you'll fall back to CPUs for those anyways. And then as soon as you get into GPUs, then you have to make sure that the GPUs are available and scalable, and you have the expertise to deal with the issues. So it complicates the tech stack also. So let's put the cost aside. Like I said, it's an important thing to consider, of course, but just let's put it aside for a second. So regardless, GPU is not a full solution. So definitely try to fix the indexing with CPUs first. Okay, CPUs first. So now you indexed everything, so your data set. So I was naive enough to think that okay, I'm done with indexing. From now on, it's going to be all incremental updates. Everything will be fine. Quickly, you realize that okay, you'll have to reindex multiple times. It could be because of maybe you want to try a new HNSW configuration, or maybe you want to try a quantization, new quantization to reduce the size and memory requirements and all that stuff. Or even like your colleague can come and say, oh, why do we have these three fields unnecessarily in this index? Just let's get rid of it. And that way our index will be smaller and faster, right? So for multiple reasons, you will have to reindex multiple times. And hopefully you won't have to upsert all these records again. That would be horrible. Okay. So one way to build a new index would be use an existing index to index so to read from, right? So you can get the content from the existing collection or index, and you build a completely new index. So which is fine, like way better than the other option. But you still like it's confusing to me. I don't know you, but it's for me it's still annoying that like I don't know when to cut off. Like I'm using an existing data set, an existing index which is live, which is getting updates and stuff, while I'm using that index to create a new one. So when do I cut off and start upserting into that new one? Like it's just not clear to me. Uh, so um, so I think that there's a problem with this coupling of like data loading and indexing. So and we should just get rid of that coupling, and we should just separate data set and index. So data set is where you have all the vectors and field, all this metadata fields, or full text fields and all that stuff. And then you keep it on as a system of record, or it's a raw format that and then you create indexes, as many indexes as you like off of that data set. Okay, so why, let's say you have index A being used for the application already live, and then you say like, oh, it would have been awesome if I can try this new configuration or new index and see if my new index performs better. You can safely create that new index, index B, and then and if you like the performance of the index B, which is also using the same data set as the source, then you can compare it exactly with the index A and index B. And if your index B is better performing, then you can just switch the application to use index B without any problem. And everything in your head is like clear, like, okay, my data set is my data source, and then I feed my indexes from my data source, and there's no confusion of like, okay, how do I move from index A to index B? How do I create new ones? When do I cut off and all that stuff? There's nothing like that. It's very simple design. So definitely go for data set index separation. Challenge number 4, balancing query latency. So each index, each application will have potentially different requirement, the latency requirement, right? Like some of them are okay with moderate latency, and some of them are even okay with uh, like starting cold, meaning my first query will be slow, but after that everything will be really good. Okay, so and why would you want to do that? Again, we're going back to the cost speed balance, right? Like, so if I can do a cold start, then I can potentially save a lot of money because I can keep my index on the cold storage until the index is being used. Like as soon as it's being used, then I will pull it into the query nodes and then start querying. So my first query, very first query will be slow, but after that everything will be super fast. So there are use cases. I'm not saying you just use it for everything, for every application. I'm just saying this should be an option because again, we're trying to balance cost and speed and accuracy. Okay, so these are different requirements. Because of these requirements, your vector database should support all these cases. It should support hot, warm, and cold start. Again, the cold start means my first query will be slow because I'm going to bring the index down to the query server and make it available. They will take, depending on the size of the index, it can take, I don't know, a couple of hundred milliseconds to a second to for the first query, and then everything will be like super fast. And potentially, so you can pick and choose which one to use for which index. And also, it would be awesome if your vector database can go from hot to hot, warm to hot, hot to warm, and even hibernate all the way to cold for a cold start, right? Like so, dynamically transitioning between these states. Or you can just say, no, just for this particular data set or index, I want it to be always hot. That means you're choosing to be a little expensive for this particular index. For the maybe others, like you're okay with a cold start, or you're okay to be always warm. Okay, so again, it's a balance of cost, speed, accuracy thing at scale. All right. Challenge number 5. This is about having okay, like how do you do that? How do you do all that stuff? How do you make that happen? So you can potentially, as we talked about it, you can potentially have like millions of small indexes. Why would you want to have millions of small indexes? Maybe a small index for each user, index per workspace, index per tenant, account. So it could be always hot. You can just say keep it warm all the time. There's no problem with that. But also like you can just potentially say hey, for my tenants or my users are not always active in the system, so hibernate the index if my user is not using it. So that why are you doing that? Again, going back to cost, speed, balance. So potentially you should be able to do that, right? Like you should be able to maintain millions of small ones, small indexes or small namespaces, whatever you want to call it. Or you can have like also massive namespaces, like one namespace with billion entry in it, billion records in it. So so that's a requirement. Like I'm talking about the requirements right now. Like so, I also don't want my query latency to suffer just because I'm indexing new records, right? Like I inserted 20 million, and then now my query latency go down. Why? Because the indexing is competing using the same CPU or RAM or whatever, and then now my queries are suffering because of that. But I don't like that. I don't want that. It's super annoying. So another annoying thing about this one is like that we ran into in the past is like how do we know how do you know you have enough SSD space? Like it's super annoying to you either allocate way more than you need and they're going to pay a lot of money for nothing. So basically, and or you're going to be keeping it tight, and then you can potentially run out of space. Either way, it's horrible. So it's just I want to be able to scale. I want to be able to store as many records as I like without having to worry about like running out of space or getting those to be like super costly for me. So that's the scaling like pain. It's super annoying. So also like I don't want my query server to slow down for an index just because there's another index that like there's another BZ index, right? So I want to be able to isolate those. Like I want to be able to say like this query should keep at 1,000 query per second while I'm launching new index, probably even with more QPS, right? Like again, scaling the queries. That's a tough one. So because of those requirements, I would highly suggest you scale each layer separately. Indexing should be separate from querying. That means you should not be indexing where the queries are happening. So and even more than that, you should be separating the indexing jobs too. So indexing happens on nodes or pods or whatever containers that are as, there, and they should not be where the queries are running. Um, so it's offloaded onto some other set of CPUs and RAM. Okay. So even the indexing job, so like hopefully you're on cloud and you should be definitely using the scalability properties of the cloud in a way that you can scale, create new indexing jobs on the fly and on demand, and scale the indexing jobs separately too. On the query also the same. You should definitely separate hot nodes from warm nodes, and you should be able to independently scale those. So scaling each piece separately, that's the whole idea. The storage is a bigger one and has other implications. So I left it for the last piece. We'll talk about it here. So as soon as we say, we're going to be using separate nodes and pods for indexing and queries, and even for the queries, we're going to have different pods and nodes for to run hot ones and warm ones and stuff. So you start thinking like, okay, then you have so many different nodes and pods all over the place. How do you move the data? How do you make sure that the index is on that query node? How do you make sure that the data set is available on the indexing node? And then send all that stuff. So how do you move the data around? So one can say like, don't move them around. Just have a cluster of n number of nodes with terabytes of SSDs on them, like and then and a good number of CPUs on them, and just scale that one single cluster as you need more CPUs and RAM. Like, okay, so this will lead to potentially poor SSD and even CPU utilization. So you might um, because you will never know if it is good enough if you have enough space or enough CPUs. You will either over allocate or poorly allocate, and you run into other problems like running out of space or queries introducing more and more latency, right? So that's looks simple, but it doesn't solve the problems. That's I think the bottom line. So the scaling, creating one giant cluster and doing everything there is looking simple and everything, but it just doesn't satisfy the requirements of the system. You just all the things that we wanted to achieve, we just cannot achieve with the system anyways. So this is not a way anyways. Like there's no way to use this as a solution. So then you say then like maybe we should use a centralized data storage. Yes, maybe. NFS maybe, EFS. Uh, so then you run into throughput limits issues, or if you increase the throughput of these systems, they usually become like insanely expensive. So and we care about throughput way more because we have tons of data. We have terabytes of data. Okay, so vectors are big. Okay, so no, so the object storage is the way to go. So now, as soon as we work with pages, like not small records and tiny little data, so each call grabs a big amount of data from the object storage. Then also all cloud providers right now, as of today, like they have like insanely good object storage solutions. So we should definitely take advantage of that to bring the cost down insanely and also and enable this a highly scalable system. You scaling indexing separately, queries separately, and making sure that we don't lose data. So object storage is a core part of this architecture. So that also means we have to insanely optimize our access to object storage. That means do whatever it takes to optimize the upload download speed, use multiple threads, multiple connections, and keep the connections live, all that stuff to make sure that you get the best out of object storage. So you have to spend time on that. Like it's not so the baseline may not be good enough. So just go like research and make sure you get you aim for 10 gigabyte per second download speed. So that's the goal. Okay. So as soon as you get to that, so then just to do the math, you'll quickly see that just bringing down an index that is less than I don't know if you um, um, less than 10 gigabyte will be less than a second. So you can have a nice cold start. Um, so anyways, just optimize for that. Optimize your access to object storage. And that will enable all the other pieces to scale nicely. That's the number 7 is more about mindset. We should be thinking about company-wide deployment of this. It's not about your index, your data set only, but the company, the multiple teams, and how do we support multiple teams. It's very likely that there will be a team maintaining the data set while other teams building applications on that data set with creating indexes with different configurations. So try to enable that. All right, at Vectara, we're trying to overcome these challenges. I think we did pretty good job for some of it, and we got rid of some of the annoyance. but we're still working on the others. As of today, if you download, if you work with Deep1B, which is a public data set, 1 billion records in it, Vectroid is able to index Deep1B, all 1 billion in less than 48 minutes. And also the latency for the query will be around 11 milliseconds. So it's doing pretty good. So we're gonna, of course, work on it more and reduce those numbers. I want to see single digit for Deep1B at least. But you can do this. You can try this yourself at our beta. So Vectora just became beta. Join our beta program. Upload hundreds of millions of vectors and see this performance yourself. Thanks so much. Thanks for listening.